Mathematical induction is one type of mathematical reasoning about a claim. Mathematical induction is used to prove statements claimed true for every positive integer n. For example, this is saying that if I add up the first n integers, it will always result in the sum of the last number times the last number plus 1 over 2. And this is a statement that is true for all positive integers n. Let's show that. So the statement S sub n, we're going to label the claim that 1 plus 2 plus 3 all the way up to adding the nth value on there is equal to n times plus n plus 1 over 2. Now, for any one value of n, we can prove that that statement is true. If I plug in n equals 1, 1 is equal to 1 times 2 over 2. That's true. If I plug in 2, 1 plus 2, or 3, is equal to 2 times 3, that's 6 over 2. 6 over 2 is 3. If I plug in 3, 1 plus 2 plus 3, okay, that's 5, 6, is equal to 3 times 3 plus 1, so 3 times 4 is 12 over 2. 12 over 2 is 6. So we see it's true for the first 3 values. We suspect that it is true for subsequent values of n. To show that, we have to use the process of induction. The principle of mathematical induction says, establish that it's true for your first case where n is equal to 1, and then prove that if we assume it's true for any random value k, then the next one, k plus 1, must also be true. Okay, that shows that it's going to be true for everything. So, our proof by mathematical induction, step 1, prove the statement's true for n equals 1. Then show that for any positive integer k, if s sub k is true, then s sub k plus 1 must also be true. Let's look at our claim. So, if I want to use mathematical induction to prove that this is true, the first thing that I do is prove that it's true for n equals 1. Okay, that's a true statement. We already showed that. Now, start with the kth statement. So 1 through k equals k times k plus 1 over 2. Now, we want to use the assumption that this is true to show that it'll be true for the k plus first term. So to do that, we're going to add k plus 1 to each side. So because remember, we were just adding up the integers. So the next one in line here would be k plus 1. But to maintain equality, if I add it to this side, I've got to add it to this side. Now, when I add it here, I'm going to want to combine like terms by getting a common denominator. So notice that in addition to getting a common denominator, I could factor out the k plus 1 that's in common. So if I take k plus 1 out of here, notice that it removes it from this term, and this term would result in a 1. So I'd have k over 2 plus 1 times k plus 1. Now get the common denominator, k plus 2, because this can be rewritten as 2 over 2 instead of the 1. So I'd have k plus 2 in the numerator over 2 in the denominator. So I have all of this equals k plus 1 times k plus 2 over 2. Now k plus 2 can be written as k plus 1 plus 1, so that I can group together k plus 1 plus 1 over 2. Now notice, this item and this item are the same, and it's the same as what's here. That's the form that I needed to have 1 plus 2 plus 3 plus n equal to n times n plus 1 over 2. This is that form where I'm letting k plus 1 equal n. So we've shown this is the n times n plus 1 over 2 equal to the sum of the first n terms. That's what we needed. So if the statement is true for the kth term, it's also true for the k plus first term. Since I established it for 1, that means it's true for 2 and 3 and 4 and every term up. So it's true for all positive integers n. Let's do it again with this one. 1 plus 2 to the first. Now notice this is 2 to the 0th. 2 to the first, 2 squared, 2 cubed, all the way up to 2 to the n is equal to 2 to the n plus 1 minus 1. So first let's show it's true for n equals 1. For n equals 1, I would have 1 plus 2 to the first is equal to 2 to the 1 plus 1 minus 1. So 1 plus 2 is 3 equals 2 squared, so 4 minus 1, that's 3. That's a true statement. Now, assume it's true for the first k terms, that the sum from 1 up to 2 to the k is equal to 2 to the k plus 1 minus 1. Now, if this is true, we're going to show it's true for the k plus first item. So, we would add 2 to the k plus 1 to this side, right? This is the s sub k plus 1 value right to here. Now, I want to show that that's equal to 2 to the k plus 1 minus 1. That would match, right, with just ending in the k plus first value instead. So, we're going to add 2k plus 1 to the one that we assumed was true. We assumed here equals here. So I'm adding this 2k plus 1 term to both sides to maintain equality. Now the left-hand side is fine. That's the way I want it to look. But over here we've got to do some work. So if I have 2 to the k plus 1 plus 2 to the k plus 1, that's the same as 2 2k plus 1s. Now, this is 2k, this is 2 to the first. So if I'm multiplying it times 2 to the k plus 1, I would add the exponents. 1 plus 1 gives me a 2, so it's 2 to the k plus 2 minus 1. Now, 2 to the k plus 2 can be rewritten as 2 to the k plus 1 minus 1, which is exactly the form that I needed. That was what I needed to show, look back right here, right? We wanted to show that this was true, that we got this form. And we show that equality here. So if this is true, then that's true. We know it's true for k equals 1, so that means it's true for k equals 2, 3, 4, every k plus 1 up. So it's true for every positive integer n, based on that principle of mathematical induction.